Hello, this is about approximation theory. Let's consider a vector space. One such an example would be the space of all continuous functions defined on an interval AB, which we denote by C of AB. And suppose that within our vector space we have a desirable subspace whose elements are suitable for approximating other elements. For example, the space of all polynomials of degree at most 5, denoted by pi sub 5, can be used to approximate continuous functions on a closed interval AB. We may ask which polynomial p from pi sub 5 approximates best the function e to the x on the interval -1, 1. What we mean by best depends on the context and how we define it, which suggests a notion of distance. In other words, we want to find the closest polynomial to the function e to the x from pi sub 5. The distance between two functions is defined in a variety of ways. Defining the notion of distance in a vector space requires adjoining a topological structure on top of the vector space structure. Then the enhanced vector space is called a normed linear space. The norm of a vector f is considered as its distance from the origin, or the zero vector, and the norm of a difference f minus g is considered as the distance between f and g. Here we introduce two such norms: the uniform norm and the least squares norm. Here we introduce two such norms: the uniform norm and the least squares norm for functions in C of AB, continuous on an interval AB. First, the uniform norm. Let f be a continuous function on the interval AB. We define the uniform norm, also called the sup norm, also called the L infinity norm, of a function f on the interval AB as this, which is the maximum of the absolute value of the function for x between a and b. So this norm indicates how far the function is from the origin, or from zero. And if we want the distance between two different functions, then we find the norm of f minus g if the two functions are f and g. For a continuous function f on an interval AB, a closed interval AB, and a given non-negative integer n, it is known that there exists a polynomial Pn star of x of degree at most n that minimizes the uniform norm f minus Pn star. And that is unique, which we call the best uniform approximation to f on AB. There is an algorithm called Remez algorithm for finding such a best approximant. Here's an example of uniform norm. We have a function cosine x. Here's a graph. It's from 1 to 4, and we want to find its sup norm or uniform norm or L infinity norm. And that is the biggest deviation from 0 from this line here. And the biggest deviation will occur here, I believe. And that's where the value of cosine, the absolute value of cosine here, absolute value of cosine of pi, that is supposed to be pi, I think. I mean, we know it's pi. It's closer to, it's probably here. Yep. And that's the biggest absolute value of cosine, because cosine is -1 and the absolute value of that is 1, and this is the biggest compared to any of the absolute value at any point from 1 to 4. The biggest happens at pi, and the norm of this function, so the norm of the cosine function on the interval 1, 4 is equal to 1. Here's another exercise, which I'm going to leave as exercise. The question is, which of the following polynomials is closer to f of x equals 1 over x? So the function f of x equals 1 over x on the interval half 2. And the two polynomials that are given here, they're both polynomials of degree 1. They're straight lines, p and q. We want to know which one is closer to 1 over x. So in other words, we need to find f minus p, the norm of f minus p on the interval half 2, and norm of f minus q on the same interval half 2. Once you calculate those norms, you can decide which one is the smaller, or they're the same, or whatever is the answer. To do this thing, you can just find maximum and minimum of the function on the interval half comma 2. Exact same way you did these problems in calculus, finding the maximum of a function, taking derivative setting equal to 0, and also you have to check the value of the function at the endpoints. And here, once you do that, you can take the absolute value of the values of the difference at the critical points and the endpoints, and then based on those results, you can tell what the norm is. The norm is the maximum of the absolute value of the difference between f and p and difference between f and q. And then once you get those two norms, then compare. Exercise 3 asks to find the best uniform polynomial approximation of degree less than or equal to 1. So you can call it P of x equals ax plus b. This is what a polynomial of degree less than or equal to 1 looks like. If a is 0, then it's a degree less than 1, which is or 0, degree 0. If a is not 0, then it's degree 1. We want this polynomial to approximate f of x equals x squared, and we know the graph of, if I draw it more carefully, the graph of this function, the parabola with vertex at the origin. So we're finding a line from -1 to 1 on the interval -1 to 1. We're finding a line such that the difference has the maximum absolute value of the difference is the smallest among all of those lines. So this one can be easily done geometrically by just thinking about what it means for the sup norm of the difference to be the smallest possible. In the next video, we will look at the other norm called the least squares norm.